Hey everyone. So we'll start with maybe a quick show of virtual hands. Who here uses Druid real-time ingestion in production? Okay. So for those of you that don't, then it's all good. We're going to start from the basics and you'll be able to understand everything. For those of you that do, we're also going to dive pretty deep and you definitely won't be bored. So tune in and hopefully you'll learn a few things. So hi, I'm Boaz. I'm a DevOps engineer at Singular. And today we're going to talk a bit about how we ran into some growing pains and scaling problems when using real-time ingestion in Druid. And we'll talk obviously, of course, about how we solved them. So first, a tiny bit of background about Singular so you can kind of understand what our challenges are. Singular is a marketing analytics platform. We pull mobile ad campaign insights from over 1,000 ad networks and process the data through a complex pipeline that runs combining and interpolation of all the data in order to provide full knowledge of our clients' return on investments, or ROI, for their marketing efforts. Additionally, we're also an attribution provider, meaning that we track events from our clients' applications and connect them with the mobile or web ad, which cause them to install the app. This enables us to provide ROI insights on a very granular level. For example, what was the return on investment for a specific creative? Our clients are ultimately companies with marketing teams, which need to retrieve their very complex and granular marketing data from dozens of ad networks. And they use our data and our systems to make data-driven marketing decisions every day. So data ingestion at Singular has a few different flows. We have our analytics flow, which works through batch, and it's what gathers data from third-party services and ingests it through batch ingestion into Druid. Additionally, we have our attribution real-time engine. That's the part that gathers stuff from mobile events and etc., and that ingests it through some large real-time pipeline that eventually reaches Druid through Druid's real-time ingestion. Now you'll notice here, Druid is our single source of truth at Singular. All of a customer's data is in Druid, and that's ultimately what they query. Our Druid cluster is customer-facing, meaning if a customer comes and uses our UI, uses our external API, internal or external ETLs, everything is going to go through our Druid cluster. So it's as customer-facing as it gets. And we've been using Druid at Singular for quite a while, since the beginning of 2017. And we have thousands of data sources with thousands of metrics and dimensions in order to give that proper granularity that we so dearly crave. There's over 35 terabytes of queryable data available in the cluster at any point. There's over 200,000 segments. And again, it's customer facing, which means we have tens of teras queried every day with over millions of queries every day. It's as customer facing as it gets. Now, a word on real-time ingestion in Druid in general. So usually when you ingest in Druid, you'll batch ingest, which means you'll essentially upload some file to S3 and then point Druid towards it as it's, and then Druid will ingest from there. With real-time, it's a little bit different. Druid can ingest from a number of different stream services. I believe Kafka and Kinesis are the big and supported and popular ones. And in our case, we use Kafka. And Druid has middle managers that are responsible for the ingestion. So these middle managers consume from Kafka and ingest into a data source, which in this case is a real-time data source. And that sits and is served on the data nodes of Druid called historicals. Additionally, there's a overlord that oversees the whole ingestion operation, and it assigns and dedicates ingestion tasks to these different middle managers. Additionally, there's something called a supervisor spec. The supervisor spec is also contains the schema for the real-time ingestion, but also tells from which topic from our stream or from Kafka goes to which data source in our cluster. So it's a one-to-one relation, and we're going to get back to that later. The only things that we do a bit differently at Singular is we have a aggregation task that ingests data from attribution into Kafka. And additionally, a real-time data source holds the last week of data for all of the customers. So usually our data is segmented in different ways. And in this case, you have all the last week of data is in a real-time data source, and then eventually we do our own handoff into the same separate batch data sources that we use for the rest of our ingestion. So this standard flow worked great for a long while until we started scaling. Our data source grew, number of segments grew, and we got to tons of segments with thousands of metrics and dimensions. And this caused latency and bottlenecks. You can see beneath me the broker query time. That graph is in minutes. The highest spike up there is like 4 minutes. So in times of intense load, we could reach a time where for a query to return would take 4 minutes, which is insane. And it's extremely correlated with the historical CPU load, which honestly makes a lot of sense. The historicals start working extremely hard to answer some query. The brokers start waiting, and if the brokers are waiting, they're not responding to queries. And since we're customer facing, this translates directly into denial of service to our customers. They're attempting to query their data, and they're not getting any response. So this is not good. And we kind of dove into why this was happening, and ultimately realized it was the real-time data source. Now, the real-time data source is a super, super hot data source. Since almost every query is includes the past week of data, then almost every query is going to hit this data source. Additionally, every query is going to use every historical. There's no segment pruning done here. And during peak times, our broker queues would build up because the historicals are working so hard to scan all of this data, and that would cause this denial of service. So if we have a data source that's a problem, and it's a problematic data source, then what do you try to do? Make it not be a problem. So we attempted to optimize our data source and try to make it less of an issue. We tried a number of different methods. We tried single dim partitioning and data compaction. Single dim partitioning, in a word, is just a way to get Druid to split the data and according to a certain tenant dimension. So in our case, it would be a tenant or a customer, and we'd be able to split within the single data source to improve data locality and hopefully allow for segment pruning to occur, so Druid could only scan some parts of the data source and not all of it. Unfortunately, this doesn't work in real time. It still requires some kind of auto compaction. And with thousands of metric and dimensions over teras of data, unfortunately, it's expensive and time consuming. Additionally, it requires every tenant to fit into a single partition, where in our case, 5% of our customers are about 60% of all of the data, and that would not work. Now, multi-dim partitioning allows you to specify another dimension to split this data further and thus solve this problem, but that still requires this auto compaction mechanism that just did not work. And we tried this. We tried this in prod, and it just took too long and didn't give the benefits that we wanted or expected. Next, we tried some kind of data compaction job. We said, okay, so we couldn't do single dim partitioning, so let's just try data compaction. Let's periodically roll up and compress our data. And we did this, and it reduced the data source size by about 30%. Unfortunately, it's very expensive with teras and thousands of metrics and dimensions, and it doesn't ultimately solve our original problem, which each query still has to go over all of the segments. So yes, we've reduced its size, and that should hopefully help some. And we tried this in prod, and it did help some, but it didn't help enough. Part of that is also partially due because we could only compact the past 6 days and not the current day of ingestion, because while these tasks would take a while, and you can't compact the currently ingested real-time data, which ultimately makes sense. So unfortunately, our attempts to optimize didn't bear fruit as we had hoped, and so we decided to just scale up. Now, it's not a bad solution, but ultimately, we didn't want to scale up our entire cluster. We just wanted to scale up the parts that would be relevant to real time. Thankfully, Druid has a really cool feature called tiering. And using Druid tiering, we were able to dedicate historicals, like specific resources, and in our case, historicals, to serve exclusively the real-time data source. And so if we were only 99% sure that the real-time data source was our problem, then as soon as we implemented tiering, you could see in the graph kind of beneath me that as soon as the real-time tier comes into play, then all of a sudden the default tier is like relax and chill, everything is okay, and the real-time tier is working really hard. The graph below me shows the CPU load of the historicals, just to clarify. And this did reduce latency spikes. We did reduce the denial of service, and it was good. It gave us better concurrency and gave us stability. It unfortunately was just very expensive. It's still scaling up, and it didn't help the query time enough because we're still scanning all of these segments. We still can't do any kind of clever pruning. And the situation is still not great. The queries are still slow. Legitimate empty queries for our customers can still take minutes to return. So like you can send a query that's legitimately going to return empty and you still wait for a few minutes, and it's a terrible, terrible feeling. And we realized we needed something just more complex. So enter data sharding. Now, sharding is a term that's used a lot in databases in general, and Druid is sharded by design. So I'll specify here, we're talking about some kind of custom applicative data sharding. What I mean by that is we have a current real-time data source that holds all of the data for the past week of our customers. So let's just split this one big data source into 16 smaller ones and evenly weight our customers by their volume. And then when any customer queries their data, then they're only going to query 1/16 of the data, essentially, instead of the whole thing. So that would require us to know how to dynamically set the target data source at ingest time and at query time, which is complex, but hopefully this would solve all our problems, and we really hoped. We didn't know. Spoiler, it did. Otherwise, I wouldn't be here talking to you today. But it is important to talk also about what didn't work and also what did work. But this did. So let's kind of jump into how we did this. So breaking this down, just to remind you, the supervisor spec is a post request that you send to the overlord, and it defines the schema for the ingestion and what topic goes to what data source. Now, this is a one-to-one relation. So if we want 16 data sources, then we need 16 Kafka topics. And so that's kind of what we're going to have to do here. Now, if we want to split our customers into different data sources or into different shards per se, what we have to do first is obviously split the data. We need to create a map of all of our customers by volume and then assign shards to each customer and mark the shard of each customer as some kind of feature flag. And we did this all through code and through scripts. And you can see here that the yellow customer is assigned to shard 5, the blue customer is assigned to shard 2, green to shard 5 as well, and so on. And once we've successfully split and packed all of our customers into different shards, then we need to dynamically set it at stream ingestion time. So the way our stream ingestion worked, and still works, but up before we got to sharded data sources, is we have our aggregation task that pulls from attribution, and it would write this data aggregated into a file, and this file is just a bunch of JSON lines. Then we'd have a fluent that reads these JSON lines, reads this file, and streams it to Kafka. So before sharding, we would stream to a single topic, let's say called events. So if we want to split this dynamically and ingest into one of 16 different topics, then we would utilize a feature of Fluent called topic key. And what topic key does is it basically says you configure, within this JSON line, you can configure a specific key, which is the topic key, and its value. And that value is going to be the topic that Fluent then sends that line to. It sends that record to. So that allows us during the aggregation task to query for the customer's configured shard, and then write that as the value in the topic key. Fluent would then read the file, read the record, see which topic to send it to, and send it to the correct topic in Kafka. And just like that, we have dynamically set which topic and which data source eventually it's going to get to. This also allowed us to do some kind of blue-green deployment, or in other words, some kind of double ingestion flow. Because we still weren't sure how this would look at the end, and we're working in prod, a real-time ingestion flow is super prod critical, because since it contains the past 7 days of data for our customers, they'll notice very quickly if something is wrong. So having blue-green deployment, or essentially being able to run this entire flow side by side to our existing flow, was critical. And so with this setup, we were able to do that very easily. The aggregation task simply wrote to another file, a new file that's not related to the original one, and we spun up a new Fluent that would stream from that new file into new Kafka topics, and those new Kafka topics would be consumed by new middle managers, and those new middle managers would write to new data sources sitting on the same historicals, but new data sources. And so like this, we were able to duplicate our ingestion flow. The downside of this is that, of course, it's expensive. The upside is that we have the ability to work in production without worrying about ruining things. So that's great and very important. It's definitely worth the money, 100%. So, okay, so we have our data split into different topics sitting in Kafka, and now we need to get it into our data sources. So on Druid's side, this is still kind of keeps the same flow as we saw in the beginning. We have our middle managers consuming from Kafka, and since everything's split into topics, then these middle managers are going to send, we have our supervisor spec, we have our 16 supervisor specs, each one configuring which topic is going to go to which data source, to which shard. And the middle managers are consuming from these topics and sending them to each shard. Now, the nuance here is that with a single topic, it's much easier to have more resources dynamically allocated to consume from them, because the way that Druid consumes from real-time sources is you have your middle managers, and they have ingestion tasks running on them, and these ingestion tasks are going to ingest from the stream. But as soon as you have, in our case, 16 topics, each one of these topics is going to be split into a number of partitions, and each one of these partitions kind of defines the concurrency level of that topic, and the number of, ultimately, how many clients, in this case the middle managers and ingestion tasks, are going to need to consume from it. So it's kind of this big resource weighting game, right? You have your concurrency level on your stream, which is your topics and your partitions, and you have a concurrency level and amount of compute resources necessary in your ingestion and in your middle managers, which is the number of middle managers and your ingestion tasks. So you do your own math and figure. Everyone needs to kind of figure out what works for them and for their scale, and ultimately just remember that there's a direct relation between the number of tasks that you have and the number of partitions and topics. We ultimately went with one ingestion task per topic, and we run a couple of ingestion tasks on each middle manager. In the beginning, we actually had set too many partitions in our Kafka topics. So we had, I think, 4 partitions instead of 2, and that put too much work on the middle managers and ingestion tasks, and actually flatlined our middle managers. Like their CPU went down to 0 and they crashed. So it was good that we had our double ingestion, because otherwise we'd have caused a lot of problems. So once you kind of do the math and weigh everything out and create a balanced Kafka stream middle manager task ingestion flow, then your ingestion's good. We have data sitting in our 16 smaller data sources, in our 16 shards. So we were able to dynamically set ingestion through feature flags in Fluent. We have balanced Kafka and middle managers, and we have many small data sources instead of one big one. Now, already we were able to start seeing some benefits, which was really nice. We saw a huge reduction in our segment count, and ultimately had better rollup and smaller data source sizes. And we're going to get into these numbers towards the end, but already here we realized that we were in the right direction. However, none of this really matters unless the queries are improved. What we needed to know, and ultimately our KPI was, are the queries faster? And for that, we have to set dynamically queries. The naive way of doing this is just to fetch the same feature flag that's at the topic and query its data source. Now, in reality, unfortunately, things are a bit more complicated. Things will get out of balance for sure. Customer volumes might change. Customers will send more events or less events. And we'll probably want to reshard and rebalance our 16 shards, which means reassigning a customer from, let's say, shard 5 to shard 2. And the problem with this is that if we, let's say, reassign from shard 5 to shard 2, then all the new data is going to be going to shard 2, but we still have the past, 5 days worth of data back in that old shard. So back in that old data source. So how do we know the last configured shard? So this obviously needs some kind of solution. And the solution is for us was to just create a DB model that saves this allocation history. This is a normal database and a relational database, SQL. And periodically, we just do the same process we did in the beginning for splitting the data, just automatically. We'd query Druid for the customer volume for each shard. We decide on a resharding strategy, do all sorts of bin packing, say that this customer is going to go to this shard, this customer to that shard, and then insert this the new shard or new topic into our allocation history DB model. And I'm going to show how that looks in 1 second. The last edge case we kind of need to talk about is new customers. When a new customer comes on, then to which shard do we allocate it? And then, again, the naive solution, pick the smallest shard and go there. The issue is that customer onboarding takes time, and it can take them up to a month sometimes to get to their full capacity of events. And then if we onboarded a bunch of customers in a few weeks, then to our smallest data source, then after a month, that tiny data source could turn into our biggest one. So things would be not balanced because they would all ramp up at the same time. And our solution to this is just select the random shard from the 4 smallest ones, and we see that this actually works and helps. So our allocation history model kind of looks like this. You have the customer, in this case the yellow customer, you have the shard allocation, in this case shard 5, and you have if it's the active shard or not. Is this a shard that we need to ingest to, yes or no? In this case it's yes. And then we have the deactivation date, which is when did this shard deactivate and become move from being the active data source, the active shard, to being an inactive one. And in this case, it's for shard 5, it's none because it's the current active one. So on ingest, it's very easy. You can just, when we want to ingest, instead of querying the feature flag, we just query this table and find the active the active shard allocation. In this case, it's shard 5, and so then we know, no problem, we just ingest the shard 5. All new data will go to shard 5. On query, it's a little bit more complicated. We need to query on the past week of data, and we query in the past week of the deactivation date. So in this case, we'd go over and we'd say, okay, the deactivation date of shard 5 is none. It's the active one, so we obviously need to query that one. The activation date of shard 2 is from 7 days ago. It's from the past week, so we need to query that one as well. Shard 0, however, was deactivated ages ago and is therefore irrelevant, and we don't need to query that. So then we just query shard 5 and shard 2 and then merge the results. So querying works. It's time to flip the switch and see what our actual benefits are. So we rolled this out to our internal test customers, into some Canary customers, and then we rolled it out to everyone. So are you ready to see the results? Boom. Okay, exciting. So the results were huge. There was a huge reduction in query time, almost 2.5 times what it used to be. The top line is the average. The bottom purple line is the medium. The middle is P75. And from the moment we enabled sharding, the query times dropped immensely, and it was just amazing to see. We had a huge load reduction across all the historicals, including those historicals that are just serving the real-time data source, but also other historicals. This is due to all sorts of concurrency bottlenecks and etc. But mostly just the whole cluster started just acting far more optimally. Our total data source size was halved. If our original data source, single data source was super big, then the sum of all these 16 are now half of what they were. The total segments is a third of what they used to be, which is amazing. And this is mostly due to the decrease in row cardinality and rollup, because customer data is more likely to be adjacent in the middle managers at ingest time. Then when it's ingested, then Druid is able to roll it up more optimally, because there's less tenancy, so there's less cardinality, and your data from the same customers are going to be sitting next to each other, so you're able to aggregate it better. And that's what really caused one of the big significant drops. The single caveat is that there is a decrease in multi-tenancy, meaning that the sort of scaling games in our ingestion flow are more complicated. It's less easy to allocate resources for ingestion, because things are a little bit more static. But once you kind of figure that out and do the math and see what works, then it's really, really, really manageable, and the benefits are definitely worth it. So to summarize, we had a frequently queried, heavy metric and dimension real-time data source that caused query time bottlenecks. We used a custom data sharding methodology to split our data sources in this one big data source into 16 evenly weighted data sources, and we got many, many, many benefits. Ultimately, real time worked up to a certain scale in terms of metrics and dimensions and size, and we ultimately made the decision and implemented a way to shard it. So, what's next now that our sharding works? So we can maybe re-enable compaction or single or multi-dim. Maybe now it'll work better now that we're split more optimally. We can also optimize our resharding algorithm. Right now it kind of moves things without necessarily needing to move things, but it works well. But it could be optimized further. And additionally, just continue our never-ending research into how to better optimize our Druid clusters and provide a better experience for our customers. So thanks so much for listening. I'm here now for any questions that you might have, but if you think of anything afterwards, feel free to shoot me an email or reach out. And once again, thank you. Any questions?